welcome everyone. Go back to our lesson. This is the next lesson for introduction to the quantum computing and the programming. Okay, so this lesson we will cover about the common mapping point and how you can represent the quantum bit 1 or 0. Okay, so let's see how it looks. So actually this guy is very interesting because you can see how you can draw a bit quantum bit in practice. Okay. Before we go to that part, so we will look more about the previous lesson. Our previous lesson already covered about we represent, you transfer between the complex vector and to the quantum space. Okay, so for example, we have a complex vector, yes, complex vector, and after we transform to the quantum space, and we have an angle, yes, this one, right? And you can represent the quantum vector on the Bloch sphere, yeah, Bloch sphere. And you only need to have two angle, yeah, the theta, and this one is phi, yeah. And okay, so now we can apply this kind of formula, try to draw our bit. Okay, recall, okay, after we transform, use a Hopf, yeah, we have Hopf, this Hopf map, right? After we transform, we Hopf map, we have this kind of formula. So, okay, after we transform, how we can draw about the qubit in the polar form or in the Bloch sphere. So, yes, this is one of one of the methods, yeah. So, if you see after we for example, we have qubit 0. Qubit 0 start it, the quantum the vector 1 and 0, right? Quantum 1 and 0. And after we transform to the complex vector, we have this kind of complex vector. So that means the real part is 1 and the imaginary part is 0, and similar for this one. And after we have a complex vector, this one. We can check x1, this x1, x0, this x1, and this is x2, and this x3, okay, this value. So you see x0 is equal to 1, right? And x1 is equal to 0, this x1. And x2 equal to 0, and x3 equal to 0, yeah. So after we have this fourth value, so you can check back something, use the Hopf, the map, and you can multiply this one. You can replace, for example, you can replace this one 1, and x2 is multiply this 0 over here, right? So similar, you can multiply with x0, multiply 0, right? Okay, so this kind of value is 0. So 2 multiplied to 0 is equal to 0, right? So this kind of, yeah. Okay, so similar, you do for this part, so you 0, yeah. So after you have, you finish about this calculation. So you have, the final vector. We have 0, 0, 1. So we have x, y, we have z, right? This x, y, z. So if you see over here, we have a Bloch sphere. If we define this, this is x, yeah, x the axis, and this is y the axis, right? And this is z, this z, or z, yeah. So over here is z is 1, right? Yeah. So this is a value, and the other x and y is 0. So if you see the arrows may go to the north pole. This is north pole. Yeah. This is how in the quantum, how the quantum state in the zero state look in the drawing or in the figure when we draw or we plot in the simulation. So how it look? Yeah. Please remember, quantum 0 equal to the we want to go to the north. Okay. And okay, now we can look more about the other way to represent in the the complex vector. Okay, we have two parts. The previous one we use this is a Hopf map, yeah, Hopf map, and this one is we use about the Euler formula. Euler formula. So Euler formula. Yeah, after we use the Euler formula, we have a same. Yeah, we have a same the value. Yeah, and if you see the value, the total. Yeah. The value after you transform, you use the Euler and use the quantum vector. We have the same the value. Yeah. So the one key point in this part to remind you, we have two ways to represent one quantum state. Okay, and one is you can use Hopf map to transfer to the three dimension. The second one you can use this one Euler and try to transfer to the angle, yes, something angle, theta and phi, yeah, okay. And this is but this one is for 0. What about the 1? The quantum bit 1. So quantum bit 1, we have a same. Quantum bit 0, we have a two-way, right? Two-way to represent. Quantum bit 1 have a same. We have a first one is you can use Hopf map, yeah, Hopf. Yeah, Hopf map. So original the quantum bit 1 is equal to 1 0, and you can transfer to the complex vector, and you replace x1. Yeah, this is x0, x1, x2, x3. Yeah, so you can replace each vector and change go to the Hopf map, the formula. And you can change x value. For example, you can change to this or right. This is 0, right? And this is this is 1, and this is 0, right? And 0. So this is 2 multiplied, and the total value is 0, so it's equal to 0. Yeah, and the similar you add, but in the quantum bit 1. Have a different. The quantum bit 2 is the last value. We have a -1. Yeah, -1. And if you want to see, we draw in the the Bloch sphere. The -1 will be changed to the south. Yeah. If you see the quantum bit 0, when we go to the north, right? This quantum bit 1 when we go to the south. That's different. Yeah, that is different. And the similar, we have the second method. You can use the Euler formula. Yes, Euler. Remember this Euler formula, right? And after we transform, we can have the same value. Yeah, you can replace this kind of value, and this theta equal to this kind of value. You can change them here, right? And yeah, you can change value to how to calculate. Yeah, how to calculate to the 0, because sin pi, right? And cos 0, so it's equal to 0. Yeah. So after you calculate based on this kind of formula, you have a same value. So the quantum bit 1 is equal to the south pole. Yeah. So south pole. So it's opposite from the bit 0. Yeah. So and we have the other part, and we have a positive quantum bit. So it's called the plus the symbol. So this is called the positive. So similar positive over here we have this kind of value from the previous lesson. Yeah, previous lesson. So after you can change through the complex vector, you can replace x or 0. No, x1. This is x0, x1, right? And x2, x3. So you can change this kind of value to the and apply the Hopf map and do similar. But over here you can see the total value as the point value. So we change, yeah, to change. So if you see over here, the arrow will be changed to the the front, right? Go to the x value, yeah. And similar, this one we have a 7 way, we have a same, yeah, have a 7 way to transform positive, the bit positive quantum. And how to draw it, so you're going to see it's the same the format. What about the negative? Yeah, this is kind of negative. I think this is negative. Yeah, this is negative. I think this is wrong. Yeah, this is negative, not positive. Yeah. So negative. So you can see negative. After you use the same methods, you can see we change about the first, and you can see the arrow when we go to the opposite way. Negative, positive when we go to this one, right? But negative when we go to this one. Yeah. So that is how different between the two parts. Yeah. This one I think is negative. Okay. So this one negative. Yeah. Okay. And for example, you can see this kind of example. You can plot the the example in the sphere, and the value of quantum, this kind of example. So you can check more in how you plot, and we can find the other part. After we have we have the quantum state represent in the in the Hopf map, so you can transfer and find the canonical state. Yeah, canonical state. So this one is how you apply the Hopf map. You can Hopf map. You can calculate the same value. Yes, this one is. Yeah. So okay, the key point over here in the summary, we have we know how to do represent. We have 0 bit, right? And we cannot know how we can plot quantum bit 0, quantum bit 1, and we can know how to draw the quantum positive, and we know quantum bit negative. Yeah, the positive and negative. Okay, that is a key point for this kind of lesson. Okay, thank you everyone.